Hello everyone and welcome to this section in which we shall be looking at image classification with the Huggingface transformers. So we are going to build a model which will take as input a plant image like this one, and then it's going to tell us whether that input is healthy. Let's increase this. It's going to tell us whether that input is healthy, rusty, or powdery. So we could take this input and we expect to have as output from here powdery. So this should be powdery. And then if we have this other input, we expect to have rusty as output from the model. Let's call this model M. And take note that we are going to use Hugging Face transformers. So here we expect this to be rusty. Let's just add that below, rusty. There we go. And then we also expect that in the case where it's healthy, like here, we expect the model to output healthy. So we have this three different possibilities. Now, if you have a different data set with, say, two possibilities or five or more possibilities, then this number of different possible outputs will differ. So that's it. This is essentially what we shall be building in this section. Now, the data set we'll use will come from Kaggle. You should know that the Hugging Face platform itself, the Hugging Face platform itself also has different data sets. So the first thing we'll do is we'll start by understanding how to take a data set from a platform like Kaggle and then converting it or loading it up in our Hugging Face data sets and then making use of it directly using the transformers library. So this is our data set right here. It's been uploaded by Rashik Rahman about 4 years ago on Kaggle. And you have different code samples which show how this data set is exploited. We are not going to look at this for now. We are focused on this data CAD. The data set contains three labels: healthy, powdery, or rusty, which refers to different plant conditions. So there is a total of 1,530 images, which are divided into the train, the test, and validation sets. You could see them just right here. So if you open up the train, you see here we have another subfolder called train. Open that up again. We see we have the healthy images. We have them here. We have the healthy images. We have the powdery images, and then we have the rusty images, and the total number of files we have per folder. So that's it for the train. We have also the validation, and then we have the test. So these are the different parts of our data set. Now, getting to the code, here we'll start by installing Hugging Face data sets, evaluate, and then we'll also use the accelerate model to speed up our computations. We are going to install this for Kaggle so that we are able to download the data set. So let's run this cells, and then we have some imports. Run this too, and we'll go ahead to download our data set. Now note that we need this kaggle.json file, which you see I've already uploaded right here. Get into the Kaggle platform, we get to settings. So we get here, settings, and then we scroll down to where we have this create new token. So when you click on create new token, you will be able to obtain the kaggle.json file, which is used or which you upload here. You see here kaggle.json, which I upload, and then when I run this now, I'll be able to download the data set. So here we have the dataset uploader, and then we have the dataset name. So that's it. If you run all these files and then you unzip this dataset into this folder, this dataset folder right here, you will be able to get your dataset just as it was on Kaggle. So we have the test, we have the train, and then we have the validation. You have your healthy, powdery, and then rusty. So that's it. We've downloaded this data set and we have the setup in Collab. Now the next thing we want to do is upload this to the Hugging Face platform. So you make sure first of all that you have an account on Hugging Face. So you could see here the different data sets. You have for almost 500,000 different data sets on Hugging Face. So all you need to do is create an account, and then once your account is created, you go ahead and generate an access token. So you could click here, you get your settings or access tokens. There we go. From here you go ahead and generate your access token, and then make use of that access token to be able to upload this data which we got from Kaggle, which we now have on Collab, onto the Hugging Face platform, so that we'll be able to make use of that very easily with the transformers library when we shall be training our model. With our data in the folder, we could now specify this data directory to create this plant data set. So here our data directory is this data set, and that's what we specify right here. We also specify that this is an image folder, so that this load dataset method understands how to treat the data that's found in this folder. You should note that this could even be data you collected yourself. So that's it. We run plant data set. You see we have number of rows exactly as we expect. And then the features, we have the image and the label. Now the image here is going to be, let's add the cell. The image here is going to be an image that we know or that we have, or whatever image. And then the label is going to be values between 0 and 2. So either 0, 1, or 2. Now we could define this 0 to be healthy. So we could have healthy, and then yeah, for 1 we could define this to be powdery, and then 2 could be rusty. So this is how we are going to understand this data set. Now we have the set, we have run this already. Now to push this to the Hugging Face hub, we are going to log in. So we have notebook login. You find that here we have this input for token. We put in the token which we created in the Hugging Face platform, and then we click on login. So that's it. Once we logged in, we give the repository name. So I'm going to call this plant dataset. So plant dataset, and then we push this to the hub. So run that, and that should be pushed to the hub. See, it takes some time. And then once that's going to be pushed to the hub, the next thing we'll do is load this data set. So we'll run this again, and then we have your full data set. There we go. So run that, and then wait for the outputs. Now that we're done with uploading to the Hugging Face hub, we could get back to Hugging Face, and we have plant data set. And let's sort by most recent. So recently updated, and there we go. So just 2 minutes ago, some other person has uploaded this data set, and 4 minutes ago we uploaded this other data set. So check this out, and we could see the different images and their labels. Now you could filter this by the label, so only healthy images will obtain only the healthy images. And then if you select just rusty images, you obtain only the rusty images. It takes a while to load, and that should be done very soon. Now that it has been loaded, we see here we have these rusty images which have been selected. Now note that the healthy images occupy 34.5% of the data set, the rusty 32.9%, and then the powdery 32.6%. So this is our outline of our data set. Now let's get back to the code. We this time around have restarted the kernel, and it should be noted that because we've already loaded our data set, or we've pushed our data set to the Hugging Face hub, we no longer need to download these from Kaggle. So let's comment these parts. We already have our data set. We can comment these parts. There we go. And let's comment all these parts. And then now all we need to do is simply get our data set, which has already been pushed to the Hugging Face hub. So we get our full data set as usual, and you see this works, or this should work just fine. Our next step will be to split our data set into the train, validation, and test sets. So supposing we have a data set which is 100%, we want to split this such that we have 80% for training, we have 20, or rather 10% for validation, and then 10% for testing. So this year, the testing and the validation form 20%. That's why here we have the 0.2. This is equivalent to 20% of the full data set. So this train rest, so we have the train data set, and then the remaining will be designed such that we'll take the full data set, we'll split this into two parts. The train will take 80%, and the remaining will be 20%. Then for the remaining, that's the train rest test part, that's the remaining 20%, we are going to split this again such that we have 50% for validation and 50% for testing. So with all this setup, we'll now have a train set, a train data set, which is going to be 80%. We have the validation, which is going to be 20%. And then we have the test, which is going to be 10%. The validation is actually 10%. So let's run this and then see what we obtain. You see that out of the 1,532, we have 1,225 for training, 153 for validation, and then 154 for testing. After splitting our data set into the train, validation, and test sets, let's go ahead and visualize a few samples from our data set. So here we specify the label names. We have the 0 is healthy, 1 powdery, 2 rusty. We want to produce 9 different images and pick randomly. So we have this random choice. Here we get the image and the corresponding label, and then we simply plot this out. So let's run this cell, and then we see what we get. We have this output, rusty, see, rusty, rusty, healthy, 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 rusty, powdery, healthy, and healthy. So this shows us clearly that we've been able to create our data set, split them up, and then now we're visualizing them and seeing that all the different images are matching with their corresponding labels. After visualizing this data, the next step will be to transform it. So let's define some transforms. The first one is going to be the trains transform. That's a transform for the train data. Reconnect. We use Torch Vision's compose, and there we go. We have random resize crop. We have random horizontal flip, and then we convert this into a tensor. And then after this, we have normalize. So we have this normalize, or this normalization layer, which we are going to apply at the end. And then on the other hand, we have the validation. For the validation, we are not going to carry out any augmentations. We'll just have the normalization. So that's it. We have our train and then the val transform. There we go. Or transforms. So we have train transforms and val transforms. That's it. The next step will be to apply those transformations on the data. So we'll define these methods, apply transforms, and what it does is for each and every image which is part of our data set, we are going to apply, or we're going to call this transform, as you see here, this train transforms. We're going to call it on the image, and then we'll return that sample. So this example here, we have this pixel values, and the vid-based model which we are going to be using in this section understands this pixel values as the images. So that's it. We have this apply transforms, and then the next we'll apply the val transforms. So here we have val transforms, and then here we have val transforms. There we go. So it's the same or similar, but the difference is that now we have the one for the training and the one for the validation. Now let's define this normalize layer. You should note that for each and every pixel value, what the normalization is going to do is it's going to take that pixel value, subtract a mean, and divide by the standard deviation. So getting back to the code, we would define this normalize layer. Let's have normalize. So we have your normalize, and then we'll have the mean. And the way that we'll obtain the mean is quite straightforward. We'll make use of the image processor, which gives us the mean value based on the data which the model was trained on. So we have this mean, and then we have standard deviation, and then we have image processor, and we have image standard deviation. So let's take this off. There we go. Okay, so let's also define this image processor. We have image processor, auto image processor from pre-trained. We have from pre-trained, and then we have the checkpoint. Now the checkpoint is exactly this one we have here. So let's just simply define our checkpoint, and then there we go. We have Google Vit base patch 16, and then it's 224 images in 21K. Okay, so that's it. And then we run this. So we run this, and then the next will be to actually carry out the application of those transforms on our train data. So we have train data now, which is equal to the train data set with transform. So we actually apply this transformations, and then we have apply with transform, and we have apply transforms. There we go. And we do the same for the validation. So val data equal val. There we go. Okay, so we have apply val transforms, and we have apply transforms for the training and the validation. Now, to take care of the batching, we'll make use of the data collector. We are going to use something very simple. So that's the default data collector, and that's it. So now we have our data which has been pre-processed and is ready for training, such that you could modify the parameters or even go ahead and add other augmentation strategies. In this section, we'll now delve into modeling and training. So let's start by defining our model. And the model we'll be using here is the model we previously spoke of. That's the Vit-based model. And we would use auto model for image classification. So from pre-trained, and then we'll specify the checkpoint. Now the number of models is 3, so that's fine. And then the number of labels, number of labels is 3. Then the ID to label has to be defined. So let's create the cell up here, and then we have ID to label, which is equal label names, which we've seen already. And then we'll define label to ID, which is where we just simply reverse this. We could print this out so you see the output. We have ID to label and label to ID. So the Huggingface transformers is going to make this process very easy. That's the process of modeling and training, as all we need to do is just define our number of output labels. We define this ID to labels. We specify the checkpoint, which we've done previously. You could see that here. It's our checkpoint. And then once you have this set, you have your model. So that's it for our model. It's going to download whatever is required. That's actually our model weights and whatever information is required. And then from here, we'll now start with the training. Our model has now been defined. Let's go ahead and define the training arguments. So here we have training arguments. And then we are going to specify the output directory. So here we have output directory, and then we have planned outputs. Then we specify the remove unused columns to be false, There we go. We have the eval strategy or evaluation strategy is set to epoch, so it's after every epoch. We have epoch. We have the saving strategy, save strategy, set this to epoch. And then we have the learning rate. learning rate, which is very important. We set that to 5 times 10 to the negative 5 minus 5. Let's just negative 5, okay. And then we have the per device train batch size. Let's just take this to 16, but we'll need to reduce this because this is going to be too much for memory. So we have this to 2, and then the gradient accumulation steps set to 4 the per device evaluation batch size set to 16 or 2. Let's reduce that to 2, and then the number of train epochs is 3, so we'll train for just 3 epochs. And then the warm-up ratio is set to 0.1. To understand the concept of the warm-up ratio, let's take this figure. So what we're saying here is, out of the total number of steps we're going to carry out during the training, we're going to leave out the initial steps for what we call the warm-up time. So we'll have this linear stage where the learning rate, because this is actually the learning rate is going to increase linearly right up to the learning rate which we'll fix. In this case, is 5 times 10 to the negative 5. So we'll increase this learning rate from 0 linearly up to 5 times 10 to the negative 5, and then we'll continue with the training process. Let's get back to the code. We have the warm-up ratio, which has been set. We have the login steps set to 10. Okay. So let's just we'll also push the model to the hub. So push the model to the hub, and we'll load the best model at the end. We run this, and then now we start with the training. Let's take this off. Okay, so take that off, run it again. We have save strategy. Let's just take this off, run that again, and this should be evaluation strategy. So here we have evaluation again. That should be fine. And then once we're done with that, now we'll define our trainer. So we have trainer, there we go, trainer. And then we have the model, takes in the model, takes in the training arguments, which we've just set, the data collector, the training data, the evaluation data, the tokenizer, and also, given that we want to compute the metrics, we'll specify a compute metrics method. Let's define the compute metrics method. We have compute metrics, and then we will take in the evaluation data. Let's just autocomplete, and then we have accuracy. From evaluate, we'll load accuracy. So that's it. Now take note that this evaluation data is made of the predictions and the labels. So this is what the model produces, and this is what we expect it to produce from our data. Now, the output from the model are not usually going to fit the way the output from the data have been set. So let's say, for example, the model gives us an output because we have a class. We have 3 classes, so the model produces 0, 1, 0, so 100 represented. And then the label here is, let's say it's a correct prediction, because the label here can be 0, it can be 1, or it can be 2. So let's say in this case it's 1. So this is a correct prediction, but for us, for this model's prediction to match with what is expected, we need to make use of this argmax method. So the argmax method is going to pick out from this the one with the highest probability, and in this case is the one with class 1. So this is going to be replaced by 1, and you see now that there is a matchup. So that's where we use, or that's why we use this argmax. And then we now make use of the accuracy that we define here to compute that accuracy, actually making use of the predictions and the labels. So let's close this up, and then we run this again. There we go. So we have defined our trainer, and then we are ready to train. So let's say trainer.train, and there we go. Now to log in, we'll use 1DB. So you could simply click on this here and get this API key, which we will need. So you log into 1DB. If you're not yet signed up, you sign up. And for me, I'm already signed up, so I'm just going to copy my API key and I'll paste out in the code, and we shall be good to go. Here's my API key. Copy that and then just paste it out in here, and that's fine. So now training is going to start, and then We'll wait for the training to complete, and then we'll get the logs from 1DB, and from there we'll move on. We're getting an error, could not infer the type of JPEG image file. Let's try to check why this error is coming up. Looking at the error, it's clear that our problem comes from at the level of the data. So let's get back again. Now that we got this pixel values, we forgot to delete the initial images. So let's delete this, delete examples image, and then we do the same for validation. So we delete examples, and then image. Okay, run that again, and now we should have our training working properly. Accuracy, trainer, and then we have train. While training, we're getting this error where we're told that the stack expects each tensor to be equal size, but we get two different sizes. So let's get back into the data part of our project. And then what we notice already clearly here is the fact that with the validation, we forgot to resize. So let's include the resize, because if you don't resize, it means that if you have two samples which are different, then you would have different shapes, and you'll get a kind of error we're getting. So we have resize. Let's get back up and then import this. So random resized, and then we have resize. So we have resize. Run that again. Get back, and this should be fine. So now we have this resize. Okay, so that's fine. Then we'll also we'll also include the test set. So let's just have here test data, test data set with transform, and then we'll apply the validation transforms. There we go. So we have that fine, and then this okay. So we have that. We have training, which is the same, and then we'll just restart the training again. The training is now complete, and you could see that we have the different training loss, validation loss, and accuracy scores for the different epochs. Now to visualize this, we'll just simply click on this link right here, and this takes us to 1DB, where we'll see all our different metrics very clearly. So looking at these plots, we have the different metrics. As we have the accuracy right here for the validation, because this is eval. We have the loss, and then for the training, we could find the loss right here. And then also the learning rate, which varies in accordance to what we had seen previously, where we have the warm up, and then the loss starts dropping slowly as we increase the number of steps. So that is it. We've trained our model, and we could now go ahead and test this out. Let's now go ahead and run a test on our test data. So we'll run this, and then we'll push our model to the Huggingface hub. So model push hub, that's it. And then we'll specify the name. In this case, it's VidPlant. So we'll run that, and then we'll head over to Huggingface, and you'll find that your model or our model has been pushed to the Huggingface hub. So this is it. You see a test loss, test accuracy, and so on and so forth. So that's it. We have our model pushed. We could check this out. Just click on this, the repo URL. There we go. We have the model card. We have the files and versions. There we go. See here, we have the different files and versions. And then let's get back to the code. Then now we'll see how to come up with a confusion matrix for the test set. So let's go ahead and we'll make use of scikit-learn. So here we have from scikit-learn, scikit-learn metrics. We'll import confusion metrics, and then confusion metrics display. Okay, so now we have the y true. Let's just complete this. Y true is what we expect, and then y pred is what the model produces. Remember, we had this output from here. So we have this outputs dot predictions, and then we make use of the argmax as we had seen previously to ensure that we are not having a 100 representation of our outputs. So if you have, in this case, these predictions, outputs predictions, and then if you just print this out, let's say we have outputs, outputs, predictions. You'd find that for every prediction that we have here, we could replace this with a one-hot representation. So this essentially is, let's place this out. So this essentially is 0, 1, 0, because the model sees that this here in the middle has the highest probability. So you can repeat this for all the rest. But in our case, we have this one-hot representation for every prediction. So that's why we make use of this argmax, and we specify that the axis is 1 with 1, and then we make sure that we go from this to a value of 1. Now, if we had 0, 0, 1, then we want to have as output 2 right here. So that's it. So that's why we have this step. Then now we have the labels. So we get the label names because it's important when we'll be plotting. And that's why we have test data. We get a future labels and we get a name. And then the next thing we want to do is come up with a confusion matrix. To come up with this confusion matrix, it's quite straightforward. We'll just we'll make use of this confusion matrix we got from scikit-learn. So we have CM. Okay, let's go autocomplete. So confusion matrix, we have y true, y pred. So y true is what we expect, and y pred is what the model produces. Then the display, that's because we want to display this very simply. So when for the display, we specify the confusion matrix, and then the display labels, we have the names which we got from here, from the data features. Then we just simply go ahead and display this. So let's run this, and we should have this. So there we go. You found that we actually had 100% accuracy, as you could see for the test. We had 100% accuracy. That's why you have for each and every class here, we have no other wrong prediction. So this is true level, this is true level, and then this is predicted level. So for the true level, we are saying that when we expect healthy, we always predict healthy. So in no other situation do we predict something other than healthy. And when it's powdery, we always predict powdery, and so on and so forth. Now for our next steps, we'll get to Huggingface. Let's close this. So we have our model card, our model URL, which we've accessed on Huggingface, and we could get to click on this, use this model, and then we click on transformers. So what we'll do is we'll just simply copy this. We have two options here actually. You could use a pipeline, which is a high level helper, meaning that all you need to do is pass in an image, and then the pipeline takes care of the rest to produce you an output. And then you could either do this, or you could load the model directly. So you could load the model and then go through the usual process of predicting the outputs from the input image. So you would have to pass an input and then process it and then pass it to the model before it predicts, and then you have the output. Whereas with the pipeline, you just need to pass the input and then you have the output straightforward. So we'll just copy this here, and then we'll get back to the code and test it out. Now before testing, what we'll do is we'll just delete this runtime. So let's delete this runtime and then start from fresh, so that you can see that we're using a model which has already been pushed to the hub, and we no longer need to train our model again. Getting back and running what we copied from the model page, we have this. Now if you put what we have from here, or what we copied exactly, let me get back so you see that. If you put what we copied exactly, you'll get an error at the level of the image processor. That's why I modified this to the original image processor we had, but the model is our model, so that's fine. And then now we have these files. Remember what we had downloaded from Kaggle. So I just picked this one. This is actually powdery. So running this, you would find that we have powdery, which has the highest score. You could randomly pick any one. That's let's say, for example, one image that's rusty. So let's copy this path and then test that out. And you see that with the pipeline, all you need to do is just specify this and you're good to go. So you see this is rusty, and it correctly sees that it's actually rusty. Before we move on, we are going to define, or we're going to design a small interface where we'll input an image. That's we're going to upload an image from our PC, and then it's going to classify using our pipeline which we just created. So let's define this method predict disease. So actually it's just image. So here we have image, and then it's going to output a string. And then if the image is known, so we want to return please upload an image. So please upload an image, and then we will have the prediction from the pipe that we have defined already here from the pipeline. So we would have this image pass into the pipeline, and then the result. Because if you look at the result from here, you will find that usually the right answer is in the is the first option we have in this list. So that's why we pick this zeroed index, and then we specify the label. So that's how we get the result. And then we return that result. So that's it. If there's an error, we simply say that an error occurred during prediction. Now, once we're done with this, this predict disease, run that. We have in this, if image is known, there we go, run that again. And then now the next will be to define the Gradio interface, because we're going to be using Gradio. So we have iFace, Gradio. Now you don't need to understand fully how Gradio works. That's not the purpose of this section. What we want to do is just show that we could actually make use already of our trained model in a simple interface. So the function here is this predict disease function. So specify predict disease. So our inputs, as we have here, is an image. We specify the type, it's a pill image, and the label will be upload plan image. And then for the output, we have a simple label, a classification result. Now let's specify the title. So here we have title. Continue with that. Plant disease classifier is healthy, powdery, or rusty. And then the description, we have upload an image of a plant leaf, and the system will classify its condition. So that's it. Now once we have this, we just need to have iFace, and we launch. So iFace launch. Let's run that and see what we get. So it'll take a little while, and we'll have an interface which is going to pop up right here. So we'll leave that to load a bit. So that's loading. Once our interface pops up, we are going to then upload an image. So let's upload this one. You have this image coming up. It's uploading. Once it's uploaded, we'll just click submit, and then we'll allow our model take care of the rest. So let's just see first of all what the image looks like. From the look of things, it looks like it's a powdery image. So let's submit, and then we classify the results. So I just randomly picked some images from the data set we have already here. Now let's wait for the model to classify the results. As you could see, the model predicts this right. The prediction is powdery. Now we could cancel this and then pick another image. Let's pick this one. And once it's done uploading again, we're going to submit. So that's it. It's just loading now. So we'll submit. And then we see the result we are going to obtain. From the look of things, let's just look at this. It looks healthy. So our result should be healthy. So we've just built this very simple interface which permits us test out our model. You see, we're able to upload an image. You could upload any image or from our data set or similar to the one we have in our data set. And we expect to have reasonable results. Hello everyone, and welcome to this new section in which we shall focus on deployment. So in the first part, we'll start by converting our already trained model to the Onnx format. And we'll look at in depth what this Onnx format is about. Then we'll run the model which has been converted to the Onnx format with the Onnx runtime. Then we'll build an API using FastAPI, which will permit us to serve our already trained model, which has now been converted to the Onnx format. Onnx, that's ONNX, stands for Open Neural Network Exchange. And this is in fact an open source format for machine learning and deep learning models. The Onnx format is one which helps us represent computational graphs. And we know that machine learning models, whether trained with PyTorch, TensorFlow, Keras, MXNet, or whatever other machine learning or deep learning library, are actually computational graphs. And so this format permits us to represent this computational graphs in a way that they could be interoperable between different libraries. So what this simply means is if we have a model trained with PyTorch and converted to Onnx, we could easily reconvert this back to TensorFlow and process or train this in TensorFlow. So this permits us to live or work with whichever library we want to work with, regardless of where the model was initially constructed or which library it was trained on initially. On the other hand, the Onnx runtime is an engine which permits us run Onnx models very efficiently and take into consideration the kind of device on which we are running these models. So generally, the converting our models to the Onnx format ensures interoperability, the model portability, because now we have models which can run on Linux, Mac, or Windows very easily or seamlessly, and even the programming language you're using too. So you could create a model or you could train a model in Python, and then you end up using that model in Java, thanks to the fact that you've converted this model to the Onnx format, and the Onnx runtime could be run in Java. So a Java developer could train a model in Python and then insert that model in the Java code and work with that seamlessly. Now we have the hardware access. So the way this Onnx runtime works is such that you could specify the kind of hardware you want to be carrying out the inference on. So if you're working on a CPU, for example, if you're working on a CPU, the Onnx format permits you to run this model more efficiently on a CPU as compared to if you're working on a GPU. Regardless of the fact that you're working with specialized hardware or not, you could always get the best out of the hardware you're using because or thanks to the fact that you converted to Onnx and you're using the Onnx runtime to run your model. Diving into the code, we'll start by installing Onnx and the Onnx runtime. So let's run that. And while that's running, we are going to go ahead and load our model, which we've trained already. So we have model, auto model for image classification. And there we go. So here's our model, which we trained previously. And then we'll specify return dict to be true. True. Okay. Now we have the processor, auto model for auto image processor, actually, auto image processor from pre-trained, and then we use the Google Vit, this Vit based patch, which we've seen already. So here we have the model, and then now we have the processor. We run that, and that will specify a dummy input because now at this point we want to create or we want to convert our PyTorch model onto an Onnx model. So we're going to create a dummy input which will be used in exporting this model into the Onnx format. So we have this dummy input that is one, that's a batch by 3 by 224 by 224. So we run that again. We have that. And then the next thing we want to do is specify the input names and the output names. So we have input names, pixel values. We've seen this already, actually. So we had this where we were pre-processing our data previously. Just want to take a look at that. So here we had this pixel values. Remember this. And then in the outputs, we have the logits. Let's take this off. So that is it. Let's get back. We have the input names, and then we have the output names, logits. So we have the set now, and then let's run this. And then now we'll do torch Onnx export, and then we'll specify the model. Let's just take all this. We'll specify the model. We have the dummy input. We have the Onnx model path, which is vit classification.onnx. The export, we said export, or we're going to export parameters. The offset version is 14. Do constant folding set to true. Input names is input names we have just defined. So we have input names, and then we have output names too. So output names, there we go. Take that off. Okay, so we have this, and then we have now this dynamic axis. So here we're specifying that this batch here, this batch axis is dynamic. So here we have this axis 0, and then for the logits also axis 0, and that's the batch size. So that's it. That's all we need to do to export our model. And once we're done with exporting our model, we could open this up to the left and check that out. So it's still exporting. Now with our model which has been exported, you could see it right here, vid classification. We'll open our data set, and then we'll pick out sample data or sample image. So let me just open this up, healthy, and I'll just copy this path. There we go, and we'll test this out. So we have this our test image, test image. We'll have image. There we go. Actually, this is what we had already. So let me just paste what I just copied now. So we have this image, our test image, and then we're going to pre-process it. So we're going to resize and then carry out all the rest. And the reason why I'm doing this is because if we pre-process using this preprocessor, when we are deploying, it means that we'll need to install the transformers library, because this is imported from transformers library. And because we want to have a scenario where all we need to do is install Onnx and Onnx runtime when we want to deploy our application, we are not going to make use of this. So take this off, and then we're going to pre-process this by ourselves. So we have our test image, and then we'll resize this image. So this is part of the processing. Resized image. We have the test image resize. There we go. We resize the image, and then we convert this into a NumPy array, and then we transpose, because let's print out this NumPy array. Let me call this np array np. Okay, so let me just comment this so you understand how this transpose works. Get a shape. There we go. So you see that when you have this input and then you resize it, you have this output, which is 224 by 224 by 3. That is height. So what we have here is height by width by 3. Now we have a model which instead takes in 3 by height by width. So what we do is we're going to transpose this and modify or change the order of the image inputs. So this height is 0, index 0, width is index 1, and then 3 is index 2. So this 2, you see, that's why we take this 2. We transpose this such that this 3 gets to the 0 position. That's why we take 2 and we put it out here. And then the height and width now follow. So 0, 1 will just follow. That's how we transpose this. So now we have image, resized image, and then here we have transposed image. And once we finish with transposing this image, the next thing we want to do is add an extra dimension. So that's why we have here expand dims. Or let's just have this image. Let's just have this as image. There we go. So we have this image, and then we expand dimension to add that extra batch dimension. So let's print out the image and get a shape. So you see, now we have that extra batch, and then we have 3 by height by width. So that's it. Let's take this off. Take this off too. At this point, the next thing we want to do is rescale our image. So we have here image, image as type float, as type np float. Okay, and then we divide by 225. So we rescale, and then it's going to be the same shape, obviously, so that's fine. So let's just run this, and we have our output image now. So this is our final image, which has been resized and rescaled. After pre-processing the image, the next step will be to create an Onnx runtime session. So we'll have session and our Onnx runtime. Let's import this first, just right up here. So we import Onnx runtime as ORT, and then we have Onnx runtime, and we'll create this inference session. Okay, And then we'll specify the model. You see here we'll specify the model, and we'll also specify the providers. So here we have providers. That's fine. Now we could specify the providers just here. So we'll create this list, and this is where you'll see how Onnx can permit us easily deploy on different hardware devices. So if you're having a CPU, you just have to say CPU execution provider. So CPU execution provider, and that's fine. And if it's a GPU, in that case you will have CUDA execution provider. So that's it. Anyway, we are gonna use a CPU here. If you check out our runtime, you'll find out we're using a CPU. This shows us how the Onnx runtime permits us run our models on different hardware more efficiently. So let's just take this out because we're gonna run this on a CPU, and we run that. We have our session. Now we'll define our session inputs. So we have our session input actually, and there we go. Okay, so we have session get inputs, and then the name, the attribute, and then we'll pass in the image. Remember the image we just had above here, which we just pre-processed. There we go, this image. That's what we pass in here. So we have our image, and then now we run this, and then now we have the Onnx output session run. So now we have defined this inference session, and then now we're about to run that. So we'll specify, yeah, we have known, and then we have our session input. There we go. So we have session underscore input. Okay, so we have our input passed in, and then now we expect it to get our output. So we have here Onnx logits, and we have Onnx output, and then 0. Okay, so we have this Onnx logits now. Take that off. Okay, so we have this Onnx logits now, and then now we could print this out so you see what that actually is. Onnx logits. So it runs our model, and then this is what we obtain. So now the next step will be to just get the one with the highest probability, which we will see clearly from here is actually this, because we already know that it's healthy. So it's been normal that the probability, the one with the highest probability should be the one with the zeroed index. So that's it. We have that, and then now we could just simply get the index by using the argmax. So we say Onnx prediction index, and then we have argmax, and Onnx logits axis 1, and there we go. So we run that. Let's just have the prediction or the pred index here. Okay, so now it predicts 0, and we could change this file. So let's get back to the test. Let's take one that is rusty and paste that out there. So let's copy this, copy path, take this off, and then we have this new path, rusty image, and there we go. You see we have 2. So our model predicts our model predictions are similar to what we had with the initial PyTorch model. So what we've done now is we've successfully converted our model to the Onnx format, and we've used the Onnx runtime to run this converted model. Welcome to the session in which we shall build and deploy our model using FastAPI. So the very first thing we want to do is to create our virtual environment. We have venv and .venv. Now we're going to activate this virtual environment once it's been created. So we have here source venv bean activate, and there we go. So once we have this virtual environment activated, the next step will be to install the different libraries and dependencies we will need. Now note that because we have converted our model to the Onnx format and we're using the Onnx runtime, all we'll need to do here is just pip install Onnx, and Onnx runtime. With Onnx and Onnx runtime installed, we'll now install FastAPI, Python multipath, because we are going to have as input images, and then NumPy and Pillow. So we have all the dependencies installed. We could now take this off and then start with the imports. We import NumPy as NP. We import Onnx runtime as ORT, similar to what we had already in the collab notebook. Now we have FastAPI. We import FastAPI file and upload file. Remember, we are actually uploading a file, that's in this case an image, and we expect the model to take this image and then give predictions. From PL, we import image. This should be image, yeah. And then we have import IO. We're also going to use the asynchronous context manager to handle the lifespan of the application. So we have context, from context lib, we import async context context manager. Okay. Now we have this. We'll specify the Onnx model path, which is what we have here, the vit model.onnx. So we just have vit model Onnx. Then we have this ORT session, which we'll set to none. Now this is actually a global variable for the Onnx session. And then we have this method, which is asynchronous lifespan. And here we have FastAPI. So FastAPI. Okay. And now we use this async. We use this async context manager decorator. We have async context manager, and that's it. And then now we will just go straight away, and in this method we'll define our Onnx runtime session. So we have, just as we had done already, ORT session is equal ORT dot inference session, and then we have the Onnx model, which is passed. So the idea here is simple. We want to be able to load this up once our API is started. So once we start our API, we want to be able to load our model and then make use of this model throughout the lifespan of our API. So long as we have our API which is up, we want this model to be loaded. We don't want to load it each and every time a user sends in an image for inference. So we just load this once at the beginning, and then throughout we are going to be using this. So now we have Onnx model path. There we go. And then once we have loaded this up, well, also note that this Onnx runtime session is global, so we just have global Onnx runtime session. Okay, so we can use this anywhere in the app. So here we have the Onnx runtime session, which has been defined, and then the next will be to yield. So once you use this yield, you are simply saying that the Onnx session or this Onnx runtime session could be used anywhere else in our API. So we are just going to yield this, and then it's only when we'll stop the API that this session will now be set to none. So that's it. So we set this session to none, and that's fine with respect to the context management. And now we have app as usual. So this is how we create a simple FastAPI application lifespan. So here we initialize this FastAPI app with a lifespan handler which we've just created right here. So the idea now is to say that anytime you're creating this app such that anytime this app is started, you would have to create this Onnx runtime session, and then you could now take in API calls from the different endpoints. And then once you are done, you can now set this Onnx session to none, and you close the app. So that is it. We have lifespan. Okay. From here, we'll move on to processing the image. So we have pre-process image, and what this takes is the image bytes. There we go. And then now we have, or we make use of this. Yeah, let me just say image. We have the pills image, and then we open up this. But the bytes, this image or this pills image doesn't take in raw bytes. So to convert the raw bytes into a format that this image will understand, we would have IO bytes IO. Okay, and then we have image bytes. There we go. And then we'll convert this to RGB. So convert this to RGB, and that's fine. Okay, so we open this up, and then we convert this to RGB, and that should be fine. So let me make sure that it's closed. Okay, so that's fine. And then the next step will be to resize, similar to what we have seen already. So we just resize, resized image, and then we do image, the resize, 224 by 224. You could obviously modify this and have an image height and image width, but let's just keep it that way, and we'll move on. We have the numpy array, numpy as array, resized image. There we go, resized image. That's fine. And then now we transpose the image just as we had seen already, and we explained previously how and why we transpose the image this way. So we have np transpose, we have the np array, and then we specify 201 just as we had discussed previously. So here we have 2, 0, and then 1, and I should close here. Okay, so we have now image expanded, or just say image expanded, yeah. Expand dems, and then we have image transposed, and axis 0. So we add that extra axis. So once we add that extra axis, the last step will just be to normalize it. So we have image which has been normalized by actually rescaling. So we have image expanded as type float 32, and we divide this now by 255, and we return the image which has been normalized. Okay, so that's it for the pre-processing step. We just need to get our image, or we need to find a way to get our image. Once our image is gotten, we pre-process it, and then we make it ready for passing into our model. So that's it for this part on pre-processing the image. Now the next step will be to design the inference endpoint. So here we have the infer. So we'll call this infer. Okay. So here we have the infer, and it's async. It's an async method. So we have infer, and then it takes in a file. And then here we have this decorator app. It's actually a post request which we're going to be making because we'll be passing in an input image. So we'll call this infer, or you could call that inference, or whatever name you want to call it. That's fine. So we have your infer, and then if the ORT session is known, we could return. Take this off. We could return error. So we could return an error. The model is not loaded. So if this model is not found there, we could just return this error, and that's it. The next step will be just to take in the image. So we have image bytes. Okay, so since it's an async method, we could use await file read. So this is the file which we pass in. We read the file, and then we obviously what you read is the pure or raw image bytes. So you get the raw image bytes, and then you pass this raw image bytes into the pre-processed or this pre-processed method we had here. So we have image pre-processed, and then equal pre-process image, and then this pre-processed image takes in the image bytes. Okay, so it takes in the image bytes, and then now we have our session input, which is similar to what we have seen already. We get the inputs, specifying name, and then we pass in the input is an image which has been pre-processed. So we have image pre-processed. Okay, that's fine. And then now we have the Onnx output. We get the Onnx output by passing this in because we want to actually carry out the inference. Take that off. So we have ORT session run. We have run known and session input, which is our actual input. There we go. That's fine. We have now we could get the logits from here. So let's just say an Onnx logits. Onnx logits is equal Onnx output index 0 output. Okay, that's fine. Now, once we're done with getting this logits, the next step will be to just get or produce some output, which is going to be quite understandable. So we would have the predicted index and then its score. So let's just have the predicted, or let's say we'll return the predicted, or let's say the predicted index, and then we'll have predicted, let me say pred index, and then we'll have the score. So we get the index and also its score. We could just leave out the score actually. Let's just have the predicted index. So we have the predicted index, and then we'll get this. The way we'll get this is pred index. We have int argmax, Onnx logits. There we go. We didn't know why we're using this argmax. Saw that already before. Specify the axis equal 1. And then we have here index 0. Okay, so that's it for the predicted index. And now we could now test this out. But before testing this out, it's always generally fine to have a root method. So let's just have this method for testing. So test API, kind of like test API method, which usually tests whether our API is live or not. So it's a simple get request. So we have that, and then we have it's just going to return something simple. So let me take this off. Okay, so we return a simple message. So we'll just say the API is live. Okay, so that's it for the two endpoints which we have created. One is a get request, and the other one is a post request. And for the get, we don't need to put or pass in anything. We just need to make that call, which is actually, this is the root actually. Make that call to root and we get this message. And then for the post request, we need to pass in an input file, and then this is expected to be used in carrying out inference by the model. Now we're done with building our API up. Let's go ahead and test this out. So we have UVcorn main, because here we have main.py, and then we have our app, and then the reload ensures that when we modify our code, we will be able to update our API automatically. Now, one thing we've added is this upload file right here, because let's take this off so you'll see the difference. Let's take that off. If we just have file and we run this, clicking on this already, you have the API is live, exactly as we expected. And then you could get to the docs. And then if you want to carry out inference, you see, click on try out. You find that you have the file doesn't permit you to pick a file very easily. So what we'll do is we'll get back here, and then we modify the code. So let's have let's get back here. Okay, so we have upload file and then file, and this now will permit us to be able to upload a file very easily. So let's save this, and you see this, the API is reloaded. And then if we get back, we will now, and we reload this, click on try out. You see, you can now pick a file. So let's pick a file, pick this image file, and then we execute. Now we have our predicted index, which is 0, telling us that the image or the plant we've passed in to the model is one which is healthy. So that is it for the section. We've seen how to convert our model to the Onnx format, make use of the Onnx runtime to run this model, and then deploy this with FastAPI.